Deep learning is a subset of machine learning that focuses on teaching computers to learn from data in a hierarchical manner, mimicking the way the human brain processes information. At the core of deep learning are neural networks, which are computational models inspired by the structure and function of the human brain. These networks consist of layers of interconnected nodes, or artificial neurons, that process and transform input data to produce an output. What sets deep learning apart from traditional machine learning algorithms is its ability to automatically learn representations of data through multiple layers of abstraction. This hierarchical learning process enables neural networks to extract complex patterns and features from raw data, leading to more accurate predictions and insights. One interesting fact about deep learning is its success in various fields such as computer vision, natural language processing, and speech recognition. For example, deep learning algorithms have achieved human-level performance in tasks like image classification and speech synthesis. The term deep in deep learning refers to the multiple layers of neurons that make up the neural network, allowing it to learn intricate patterns and relationships in the data. As a result, deep learning has revolutionized industries such as healthcare, finance, and autonomous driving by enabling machines to make decisions and perform tasks that were once thought to be exclusive to human intelligence. In essence, deep learning represents a powerful tool for unlocking the potential of artificial intelligence and driving innovation across diverse domains. Neural networks are the fundamental building blocks of deep learning, serving as the backbone of complex artificial intelligence systems. These networks are inspired by the structure and function of the human brain, with interconnected nodes that work together to process and analyze data. At the core of a neural network are artificial neurons, also known as nodes, which receive input, apply weights to the input, and pass the transformed information to the next layer of neurons. The connections between neurons are represented by weights, which determine the strength of the relationship between inputs and outputs. Through a process known as forward propagation, data is fed into the neural network, and computations are performed at each layer to generate an output. This output is then compared to the desired target, and the network adjusts its weights using a process called backpropagation to minimize the error and improve its predictions. One fascinating aspect of neural networks is their ability to learn complex patterns and relationships in data, enabling them to make decisions and predictions with a high degree of accuracy. Neural networks can be designed in various architectures, including feed-forward neural networks, recurrent neural networks, and convolutional neural networks, each tailored to specific types of data and tasks. Feed-forward neural networks are the simplest form, where data flows in one direction from input to output, making them suitable for tasks like image classification. Recurrent neural networks, on the other hand, have connections that form loops, allowing them to process sequential data such as time series or natural language. Convolutional neural networks are specialized for tasks involving images, using filters to extract features and hierarchically learn patterns. The versatility and adaptability of neural networks have led to their widespread adoption in diverse fields, from healthcare and finance to autonomous vehicles and robotics. As researchers continue to explore new architectures and techniques, the potential applications of neural networks are limitless, paving the way for advancements in artificial intelligence and machine learning. Neural networks come in various types, each designed to tackle specific types of data and tasks. One of the most common types is the feed-forward neural network, where data flows in one direction, from input to output, without any loops or cycles. This type of network is simple yet effective for tasks like image or speech recognition. Recurrent neural networks, RNNs, are another type that is well suited for sequential data, such as time series or natural language processing. What sets RNNs apart is their ability to retain memory of past inputs through feedback loops, making them ideal for tasks requiring context or temporal dependencies. Long short-term memory, LSTM networks, are a specialized form of RNNs that address the vanishing gradient problem, allowing them to capture long-range dependencies in data. LSTMs have been particularly successful in tasks like speech recognition and language translation. Convolutional neural networks, CNNs, are specifically designed for processing grid-like data, such as images. CNNs use filters to extract features from the input data and hierarchically learn patterns, making them highly effective for tasks like image classification and object detection. Generative adversarial networks, GANs, are a unique type of neural network that consists of two networks, a generator and a discriminator, that are trained simultaneously. GANs are used to generate new data samples that are indistinguishable from real data, making them valuable for tasks like image generation and data augmentation. Autoencoders are neural networks that aim to reconstruct the input data at the output layer, learning a compressed representation of the data in the process. These networks are useful for tasks like data denoising and dimensionality reduction. Each type of neural network has its strengths and weaknesses, and choosing the right architecture depends on the specific requirements of the task at hand. As researchers continue to innovate and explore new architectures, the potential applications of neural networks are expanding, driving advancements in artificial intelligence and machine learning. Training neural networks is a crucial step in the development of artificial intelligence systems, as it involves optimizing the network's parameters to make accurate predictions. The training process typically consists of two main phases: forward propagation and back propagation. During forward propagation, data is fed into the neural network, and computations are performed at each layer to generate an output. This output is then compared to the desired target, and the network calculates the error between the predicted and actual values. Backpropagation is the process of updating the network's weights to minimize this error, using optimization algorithms like gradient descent. One interesting fact about training neural networks is the concept of overfitting, where the model performs well on the training data but fails to generalize to unseen data. To combat overfitting, techniques like regularization, dropout, and early stopping are employed to prevent the network from memorizing the training data. Another challenge in training neural networks is the vanishing or exploding gradient problem, where gradients become too small or too large, hindering the network's ability to learn. To address this issue, techniques like gradient clipping and using activation functions like ReLU are used to stabilize training. Transfer learning is a powerful technique in training neural networks, where pre-trained models are fine-tuned on new tasks, saving time and computational resources. This approach is particularly useful in scenarios where labeled data is limited or when training from scratch is not feasible. As neural networks grow in complexity and size, training them becomes computationally intensive, requiring specialized hardware like GPUs or TPUs to accelerate the process. The training of neural networks is an iterative and resource-intensive process that requires careful tuning of hyperparameters and monitoring of performance metrics. By understanding the intricacies of training neural networks, researchers and practitioners can unlock the full potential of artificial intelligence and drive innovation across various domains. Deep learning has found a wide range of applications across various industries, revolutionizing the way tasks are performed and insights are derived. One of the most prominent applications of deep learning is in computer vision, where neural networks are used to analyze and interpret visual data. For example, deep learning algorithms have achieved remarkable success in image classification tasks, surpassing human-level performance in distinguishing objects and scenes. This has paved the way for applications like facial recognition, autonomous vehicles, and medical image analysis. In healthcare, deep learning is being used to diagnose diseases from medical images with high accuracy, aiding in early detection and treatment planning. Another fascinating application of deep learning is in natural language processing, NLP, where neural networks are employed to understand and generate human language. Chatbots, language translation services, and sentiment analysis tools are just a few examples of how deep learning is transforming the way we interact with technology. Deep learning has also made significant strides in the field of reinforcement learning, enabling machines to learn complex behaviors and strategies through trial and error. This has led to advancements in robotics, gaming, and autonomous systems, where agents can learn to navigate environments and make decisions in real time. Financial institutions are leveraging deep learning for fraud detection, risk assessment, and algorithmic trading, improving efficiency and security in the industry. The entertainment industry is also benefiting from deep learning, with recommendation systems using neural networks to personalize content for users based on their preferences and behavior. One interesting fact is that deep learning is being applied in environmental monitoring, where satellite imagery and sensor data are analyzed to track deforestation, climate change, and natural disasters. By harnessing the power of deep learning, researchers and practitioners are pushing the boundaries of what is possible, driving innovation, and creating new opportunities across diverse fields. One of the key challenges in deep learning is the need for large amounts of labeled data to train neural networks effectively. Data annotation can be time-consuming and expensive, especially in domains where expert knowledge is required. Another challenge is the interpretability of deep learning models, as neural networks are often seen as black boxes that make it difficult to understand how decisions are made. Researchers are actively working on developing techniques to explain and interpret the inner workings of neural networks, increasing transparency and trust in AI systems. The computational complexity of training deep learning models is also a significant challenge, requiring high-performance hardware and specialized accelerators like GPUs and TPUs. This can limit the accessibility of deep learning to researchers and organizations with limited resources. Additionally, the lack of generalization in deep learning models poses a challenge, as networks trained on specific datasets may struggle to perform well on unseen data. Addressing this issue requires techniques like data augmentation, transfer learning, and regularization to improve the robustness and adaptability of neural networks. Despite these challenges, the rapid advancements in deep learning continue to push the boundaries of artificial intelligence, driving innovation and unlocking new possibilities across diverse fields. The future of deep learning and neural networks holds immense potential for driving innovation and transforming industries. One exciting direction is the development of more efficient and scalable deep learning architectures to handle increasingly complex tasks and larger data sets. Researchers are exploring novel network architectures, such as transformers and graph neural networks, to improve performance and enable new applications in areas like drug discovery, climate modeling, and autonomous systems. Another interesting trend is the integration of deep learning with other fields like reinforcement learning, meta-learning, and causal reasoning to create more robust and adaptive AI systems. This interdisciplinary approach is leading to breakthroughs in areas like robotics, personalized medicine, and natural language understanding. The democratization of deep learning tools and resources is also shaping the future landscape of AI, making it more accessible to a broader audience. Open-source frameworks like TensorFlow and PyTorch, along with cloud-based services, are empowering researchers, developers, and businesses to experiment with deep learning models and deploy them at scale. One key challenge for the future of deep learning is addressing ethical and societal implications, such as bias in AI systems, data privacy concerns, and the impact on jobs and society. Researchers and policymakers are working to establish guidelines and regulations to ensure the responsible development and deployment of AI technologies. As deep learning continues to advance, there is a growing emphasis on interdisciplinary collaboration and diversity in the field. Bringing together experts from diverse backgrounds, including neuroscience, psychology, and ethics, can lead to more holistic and human-centered AI solutions. The future of deep learning and neural networks is bright, with opportunities to revolutionize healthcare, transportation, education, and beyond. By embracing innovation, collaboration, and ethical considerations, we can harness the full potential of AI to address complex challenges and improve the quality of life for people around the world. In healthcare, deep learning is being used for medical image analysis, such as detecting tumors in MRI scans with high accuracy. In finance, neural networks are employed for fraud detection, analyzing transaction patterns to identify suspicious activities. Another fascinating application is in autonomous vehicles, where deep learning algorithms enable cars to navigate and make decisions in real time based on sensor data. In the entertainment industry, recommendation systems powered by neural networks personalize content for users, enhancing user experience. These real-world examples showcase the diverse applications of deep learning and neural networks, highlighting their impact on various sectors.